All right, let's get right into it. We are right on the edge of this huge electric revolution, right? But everything, it all runs on batteries, which, don't last forever. So what if we could use AI, not just to make our phones smarter, but to make the very thing that powers them last longer and work better? Today, we're going to look at some really cool research that suggests a whole new way of thinking about exactly that. Just to give you a sense of the scale we're dealing with here, think about this number. By 2030, experts are saying there could be over 300 million electric vehicles out on our roads. Every single one of them is powered by a lithium-ion battery. And that's not even counting our laptops, our phones, or the giant batteries we need to keep our power grid stable. It's massive.
And yeah, that brings us to the real problem, doesn't it? When a battery starts to degrade, it's not just some small inconvenience that means your phone dies a little faster. In an electric car or, say, a power grid, a sudden battery failure can be incredibly expensive and, honestly, pretty dangerous. So being able to accurately predict a battery's health, well, it's become one of the most important engineering puzzles of our time.
Yeah, we're not just talking about the one battery in your car, we're talking about a future with literally billions of them. And we need to know in real time how every single one is doing. This is absolutely crucial for safety and just plain reliability, but it's also the key to something bigger. A circular economy, where we can take old EV batteries and give them a second life storing solar and wind power.
So, to manage all this, engineers are focused on two key vital signs. The first is called state of health, or SOH. You can think of this like a battery's current blood pressure. It tells you exactly how it's doing right now. The second is remaining useful life, or RUL. This is more of a long-term forecast, predicting how many more charge cycles it has before it's time to retire it. You absolutely have to know both.
So how do we actually track these vital signs today? Well, we use AI. Specifically, these really powerful models called deep neural networks, or DNNs. A good way to think of them is like digital lifeguards, just constantly watching the data, the voltage, the capacity, trying to spot any sign of trouble before it's too late.
And for a long time, the thinking in this field was pretty simple. Bigger is better. The assumption was, hey, we've got a super complex problem, so we need a super complex, computationally massive AI to solve it. Just throw more data at it, make the model more intricate, and you'll get a better prediction. That makes sense, right? Well, what if that's completely wrong?
And this is exactly where this new research comes into play. The authors suggested that instead of just building bigger, more powerful AI, we need to build smarter AI. So they came up with a whole new framework for thinking about this, and they broke it down into 4 key design ideas.
Now, what's really cool here is that this gives us a totally new way to think. It's not just about chucking a bunch of data into a black box and hoping for the best. It's about being thoughtful, about designing the AI's core pieces with a purpose. Let's walk through what each of these means. So first up is adaptability. An AI model might get trained on thousands of batteries in a perfect lab setting, but the battery in your car, it's unique. It has its own history. Adaptability is all about how well that AI can adjust and personalize its predictions for the one specific battery it's watching in the real world. Next, you've got complexity. This is all about how powerful the AI's architecture really needs to be. Does it really need a massive, super deep network to find the tiny little patterns and voltage curves? Or could something much, much simpler do the job just as well? Maybe even better?
Then we have memory. See, a battery's health today is a direct result of its entire life story. So how does the AI remember all that? Does it need to recall every single charge cycle from day one, or can it make a great prediction just by looking at the more recent past?
And finally, there's synergy. Remember those 2 vital signs we talked about, SOH and RUL? Synergy asks a really basic question. Should we try to build one giant jack-of-all-trades AI that predicts both at the same time? Or should we build 2 smaller, specialized AIs that are each an expert at their one specific job?
Okay, so armed with this new 4-part framework, the researchers put that old bigger is better idea to the test. And the results, well, let's just say they were not what anyone in the field would have expected.
This quote just nails it. The common belief was that a single super complex AI trained to do everything, predict both short-term health and long-term life, that would be the holy grail. But when they actually tested this, the data told a very, very different story.
Okay, let's look at the evidence. In this table, just remember a lower error score is way better. So for predicting that long-term life, the RUL, a specialized model totally crushed the big, complex, one-size-fits-all model. But here's the really mind-blowing part. For the short-term health, the SOH, a much simpler, lightweight model wasn't just a little better, it was an entire order of magnitude more accurate. It's kind of wild. To put a number on it, on the biggest data set they ran, this new lightweight model cut the prediction error for state of health by a jaw-dropping 91%. 91. This wasn't just a tiny improvement, it was a fundamental shift in understanding.
And you don't even have to be a data scientist to see the difference here. On the left, you see the predictions from the more complicated model. On the right, that's the much simpler ESN model. Just look at how much cleaner and tighter the predictions on the right are. It's a total visual knockout. It proves that simpler and more specialized can be way, way more precise.
And if you thought that was impressive, get this. The model that was way more accurate was also unbelievably more efficient. I mean, look at this. The big complex model took almost an hour to train. The lightweight, super accurate one, a little over 2 seconds. 2! That's not just faster. That's a complete game changer when you think about putting this tech into actual cars and devices.
So, okay, this is all fascinating science, but why does it actually matter to you and me? Well, the implications are huge, and they touch everything from the car you might drive to your monthly power bill.
This kind of breakthrough has this amazing ripple effect. First off, it means safer and more reliable EVs, because the systems inside them can be way more precise about battery health. Second, it makes it cheaper and more effective to reuse old EV batteries, which helps make our whole power grid more stable. And finally, because the AI is so much more efficient, it just speeds up the whole pace of innovation for our entire energy system. And here's one last really important point. Most of the time, the AI models that big companies build for batteries are trade secrets kept under lock and key. But the researchers here, they made all of their work completely open source. By sharing everything, they're helping the entire community of scientists and engineers move forward, together and much faster.
Which really brings us to the main takeaway here. We get so obsessed with this idea of making AI bigger, more complex, more powerful, just brute force. But what this research really shows is that the real genius, the real breakthroughs, can come from thoughtful design, from using the right tool for the right job.
And that leaves us with one last thing to think about. In a world that is just racing to build bigger and bigger AI, what other massive problems, whether it's in medicine or climate science or discovering new materials, are just sitting there waiting to be solved, not with more brute force, but just by being a little bit smarter?